One of the topics that students struggle with is passive diffusion, and that is the movement of molecules across membranes. And this is a movement that occurs without any energy being put into the system, so this is referred to as spontaneous movement. With passive diffusion, we have two different types of driving forces we'll talk about. The first is chemical. The chemical driving force is simply based on the concentration gradient, or the concentration of that molecule on the two sides of the membrane. Molecules spontaneously, again without any energy, want to move from an area where they're in very high concentrations to areas of lower concentration. So if we look at our two examples on the bottom of the slide, our red spheres have a higher concentration of panel A inside the cell compared to the extracellular fluid. So in this instance, those red spheres, the chemical driving force is going to be for those to move out of the cell. Looking at panel B, we have the opposite scenario where the red spheres clearly have a higher concentration in the extracellular fluid compared to the intracellular fluid. So in this instance, the chemical driving force is going to drive the red spheres into the cell, and these processes will occur until the concentration inside the cell matches the concentration outside the cell. So again, looking at this in our figure on the left, we can see again C1 has a very high concentration on the left side of our beaker, so it's much higher than C2. And so what we're seeing is a movement of the molecules, in this case from the C1 side to the C2 side. What this figure is pointing out and reminding you is that the molecules are always moving in both directions. So we do also have some movement of molecules from the C2 side to the C1. But if you look at the thickness of the arrows, that's reflecting the rate or the extent to which the C1 molecules are moving to C2. The thickness of this arrow for the C1 to C2 direction is much larger than the reverse process, meaning, maybe you have 10 orange spheres moving from the C1 side to C2 side and just one sphere moving from C2 to C1. So this process will continue until we reach equilibrium, which is the beaker on the right-hand side. At that equilibrium, the concentrations on both sides, the C1 and C2 side, will be the same. And also at equilibrium, our rates going from the C1 side to C2 side and the rate going from the C2 to the C1 side will be the same. That means there's no net flux. Molecules are still moving. It's just you have the same number moving from the left to the right as the right to the left, so there's no net change overall. And that's what the figures on the right are illustrating. At equilibrium in the top panel, we see we have a 1 molar concentration of those blue spheres on each side of the membrane. So we have two arrows of equal thickness representing an equal movement or rate of movement from side 1 to side 2 as we have from side 2 to side 1. So no net flux in that panel. In contrast with the bottom panel, notice we have a higher concentration on the left-hand side, 2 molar, than we have at the right-hand side, 1 molar. So again, we have our movement occurring in both directions across that membrane. However, the movement from side 1 to side 2 is larger than the reverse process. So our net flux occurs with the concentration gradient, where we're going to see a movement of molecules, a net movement from side 1, where we have a high concentration, to side 2, where we have a lower concentration. So if we take the example of some of our known biological solutes that we'll deal with, this is a table looking at the intracellular fluid concentration, or ICF, compared to the extracellular fluid, or ECF. And so if I were to ask you what the net movement would be for each of these solutes just based on the chemical driving force. All you care about is the chemical concentrations. We're not concerned about the charges associated with any of the molecules. All we simply care about is the concentration difference between the intracellular and extracellular fluid. So if we'll go down a few of these. So with potassium at the top, we see our concentration inside the cell is greater than the extracellular fluid. So our potassium is going to favor moving out of the cell through this passive spontaneous process. Again, we're looking at chemical only, chemical driving force only. In contrast, we see the next one with sodium. The extracellular fluid has a higher concentration than the intracellular. So in this case, sodium is spontaneously going to want to enter into the cell. Magnesium, we see the same higher extracellular concentration compared to intracellular. So that will also prefer to move into the cell spontaneously. Again, that's going to be the same for calcium, chloride. So these are both in, bicarb, also in. Let's look for another example. Here we have one. Phosphate has a higher concentration inside the cell than outside, so that would want to move out. And we'll just look, our last example we'll do is glucose. And this example has a higher concentration extracellularly compared to intracellularly, so it wants to move in. So for most of the questions, I do break down and ask you the spontaneous direction based on both chemical driving forces, which we've done here, which we've looked at here, as well as the electrical. So the electrical, let me go a step back. So while this chemical force will apply to all of our molecules, this electrical driving force will only apply to charged molecules. So neutral molecules such as glucose or water, we don't need to worry about this electrical driving force since they're neutral molecules, it won't apply to them. This will apply, though, to our charged molecules such as potassium ions, chloride ions, sodium ions. And with the electrical driving force, we're looking at the charge difference. So molecules are going to want to move or are attracted to the opposite charge. So something with a positive charge is going to want to be somewhere with a negative charge. Like charges repel. So this happens when you work with magnets. So the opposite, the magnet attracts. If you flip the magnet to where it's like charges, you feel that push against. They repel one another. So that's the same principle here. In general, there typically is a voltage difference across a membrane where the intracellular inside the cell is typically somewhat negative compared to the outside of the cell. And so that's illustrated here. And what that's going to mean is ions that have a positive charge are going to want to spontaneously move or be located inside the cell where it's negative compared to the outside. And we see vice versa. Something with a negative charge is going to want to move out of the cell to a more positive environment. And our rate will be based on the magnitude of the difference. So how big is the positive charge? How great is the difference between the two? We're not going to get into those more detailed calculations. I'm just looking for you to recognize something with a positive charge is going to want to be in the cell because it's somewhat negative. Something negatively charged is going to want to be outside the cell because of the negative charge. And so if we take a look at those same solutes, we're not concerned right now with any of the concentrations. All we're interested in is the charge. And so we said we have a negative, our membrane potential is negative. So inside the cell is negative, outside is positive. So we'll just simplify it to that. So our potassium with a positive charge is going to want to be move into the cell to be with the negative charges. Again, sodium, positive charge, that's going to want to be in. Magnesium will move in. We'll just skip ahead here to a couple. Chloride, negative charge, will want to move out. Bicarb will want to move out. Phosphate is also, it's not shown, but there is a negative charge on phosphate, out. We'll look at so our amino acids, proteins, we're not going to worry about those. Those are more complicated because they have multiple charges associated with them. I do want to look at glucose, though. Glucose is a neutral molecule, right? It just has a carbon ring, and it's got some hydroxyl groups, but there's no charge on glucose. So this is not going to be affected. So there is no electrical driving force associated with glucose. That's strictly going to be driven with the chemical driving force or the concentration gradient. So for any molecule that actually does have an electrical charge associated with it, the net driving force or net movement will actually include both of those driving forces. So our total force will be what's known as the electrochemical driving force. So that takes into account both the contributions from the chemical driving force, which we said is the concentration gradient, and the electrical driving force, which is the charge difference. So looking at these two examples we have here, with potassium, we have a chemical driving force moving potassium out of the cell. That's based on the concentration difference, where it has a high concentration inside, lower concentration outside. Our electrical driving force, we said, is going to favor, it's just based on charge. Where the inside of the cell is negatively charged, something positive is going to want to move in. So even though that's going against the chemical driving force, our electrical driving force is moving potassium into the cell. And what you'd need to do to determine the kind of net movement or the electrochemical driving force, you'd need to actually quantify both of those, what you get from the chemical driving force and the electrical, to give you, this is your net electrochemical driving force. And as you change the charge difference between the inside and outside of the cell, that electrical driving force can get stronger or weaker. So in our top panel, we see the net electrochemical driving force moving potassium out of the cell. In our bottom, it's going to be moving into the cell. I'm not going to get this detailed and ask you to calculate the exact components or exact contributions to determine a net. I just break it down and have you tell me chemically, is this favored to move in or out of the cell? Based on the electrical driving force, is it favored to move in or out of the cell? We're not going to get very detailed and have you determine which of those factors has a higher contribution. So another molecule that's going to move through passive diffusion across the cells, of course, is water. And when we look at the passive diffusion of water, we do have a special term, right? The movement of water is osmosis. This, as I said, is also a passive process. So water is going to be moving with the concentration gradient or down the concentration gradient. A lot of focus to this point has been on the solute side, or what's dissolved in the water. But we also do need to think about what happens with water itself. So if we look at our top figure here, we have side 1 and side 2. Let's take that back. Whatever side has a higher solute concentration is going to have a lower water concentration, right? And that's because every time you add a particle or solute to the water, you're diluting the water, essentially. So in this case, we can actually, our solute and water concentrations are provided, so you can see them there. On the side 1, our solute concentration is 0.3 molar. On the right side, it's 0.5 molar. And you can see just the impact of that on the water concentration. So our water concentration on the left-hand side, 55.2 molar. The right side, just 55 molar. So side 2 is lower in water concentration. So what that means is our water is going to want to move from side 1 to side 2. And again, that's our net movement. This is going to happen until we're at equilibrium, where again the water is free to move in both directions. When we reach equilibrium, the rate moving in both directions is the same. So that's, the same principle we saw with the chemical driving force with the ions and glucose that we looked at. It applies to water. It's just we're not used to thinking about the water concentration. Our focus is usually on the solute. The types of questions I normally ask on this is to see if you're able to basically match the osmotic pressure of two different solutions. So in this scenario, let's say we have cells, and this is always the scenario I'm going to give you. I just changed the numbers. So if we have our cells in a potassium chloride and sodium chloride solution, remember that with our osmotic pressure, it was our RT times IC. Our I is the number of particles that our solute is going to dissociate into, and C is our concentration. What I do, rather than just having you calculate the osmotic pressure at a single, for a single solution where you'd use the RT and the IC, I usually have you try to make something that's isotonic with what you're working with, or isoosmotic with what you're working with, and so the RT term will drop out. So when we're looking at having the osmotic pressure of your initial cell solution equal to the solution you're moving into, we're just interested in the IC terms. All right, so I'm going to erase that for now. All right, so in this scenario, our KCl, when we put it in water, is going to dissociate into a potassium ion and a chloride ion. So that means our I is going to be equal to 2. With sodium chloride, we're going to go to a sodium ion and a chloride ion. So we have two different ions there. So again, our I equals 2. For sucrose, if you're not familiar, sucrose is just a sugar molecule. It's a neutral molecule, so it's not a salt form. It's not going to dissociate. So sucrose just stays sucrose. There is no dissociation. So in that case, our I is equal to 1 because we just have that one single molecule or solute when we put it into solution. So what we're going to do if we want to have essentially the combination of potassium chloride and sodium chloride equal to our sucrose, so we want the IC for sucrose to equal the IC of KCl plus the IC of NaCl. We said our I for sucrose is 1, so we don't even have to worry about that. So our concentration of sucrose is going to be equal to our I for potassium chloride, which is 2, times it's 0.1 molar, plus we said our I for sodium chloride is 2, times that's also 0.1 molar. So our concentration of sucrose to be isoosmotic is going to be equal to our 0.2 plus 0.2 molar, or 0.4 molar. Okay, so that's what we would need to do to solve for that concentration of sucrose. So in that example, we were looking at a permeant solute. So both the potassium chloride, sodium chloride, sucrose are all able to passively move across the membrane. Well, if I can go back, let's see if we can erase some of this writing. I want to look at the bottom panel where we're looking at albumin in the beaker. So in this case, albumin would be an impermeant solute, meaning it cannot move across the membrane. So in this scenario, the only thing that can move across the membrane to get the two sides to an equilibrium is water. So what we can see in the left-hand side, we have a 5% albumin solution. On the right, we have a 10%. The albumin is a protein, so it's too large to pass through the membrane itself. So what you see is water moving. So water is going to move, again, we see it moving in both directions. With it favoring, we have a higher rate where the water is moving with its concentration gradient, so from high concentration to low. Remember, the concentration of water is opposite of the solute, so if our albumin has a low concentration on the left-hand side, that means water has a high concentration. Albumin on the left-hand side is high in concentration, so water is low. So water is going to move from the low albumin side to the high albumin side until we reach equilibrium and both sides are equal. So you notice now we have both sides are in equal concentration of albumin, 7.5%. Our water's equal. You notice the arrows in both directions. Arrows have the same thickness moving in both directions, indicating equilibrium. But one of the things you also note here is that unlike our previous examples where the solute was able to move, the beaker, the two levels remain the same on both sides of the membrane. But if you notice here, we have the water level on the left-hand side is lower than the water level on the right-hand side. And that's because of the albumin not being able to move. We are going to alter the volume of whatever you're looking at. And so to look a little more closely at that, in this example, again, we're looking at an impermeant solute. So that means that solute is not capable or able to pass through the membrane. So the only thing that can move in that scenario then is water. So if we look at our panel A, we have a 300 milliosmolar solution inside the cell, and that's your typical, what we use as our standard osmotic concentration or milliosmoles of inside the cell. 150, so lower concentration outside the cell. That means that water is at a higher concentration outside the cell than inside the cell, so it's going to move inside the cell with its concentration gradient. What ends up happening is we're going to alter our cell volume. So you can see the cell has now expanded its size in order to accommodate that water to give us an equilibrium concentration. So in that scenario, we're going to end up with 150 milliosmolar both inside the cell and outside the cell. If we look at our bottom panel, what we're looking at is the opposite scenario where inside the cell, and we refer to these solutions where it's the outside solution has a lower concentration, that's solute, that's hypotonic. In this bottom panel, we're having a hypertonic or osmotic solution. So in this instance, what we're going to do is the water that is at a higher concentration inside the cell than outside. So the movement is going to be from the inside to the outside. You'll notice now we get to equilibrium. But in this example now, our cell has shrunk because it's lost that fluid, and that solute is not capable of traversing across the membrane. And there are, obviously, under physiological conditions, you're often in the scenario where you have a combination of both permeant, meaning able to cross the membrane, and impermeant solutes that can't cross the membrane. And so these figures are illustrating that where with our urea is capable, that's a permeant solute, it's able to cross the membrane. If we start with a cell that is at the same milliosmolar concentration, but it has a impermeant solute, you will see urea want to move in. Urea wants to get to an equilibrium concentration outside the cell. But that, since it also has those purple impermeant solutes in there, what's going to end up happening as the urea moves in, it's going to alter the concentration inside the cell. So to counteract that, we'll also see water flow movement. So we see the cell size expanding. So there is a difference between osmolarity and tonicity. With osmolarity, you're looking at the concentration of both permeant and impermeant solutes. With tonicity, we're just looking at the concentration of impermeant solutes relative to the intracellular fluid. I'm not going to really ask you questions to distinguish. I'm just really going to have you be able to tell me whether or not our cell volume is going to be affected by changes in concentrations, and look at our earlier calculations where we were calculating something to be have the same osmolarity. So that's going to wrap up this topic, and I hope that was helpful for you.